called halogens and noble gases. You have so far covered all the p block elements along with the s block elements. This is a topic from inorganic chemistry where we will be covering and actually winding up with the p block elements, that is noble gas and the halogens. Halogens come first and then the noble gas. So let me take up the halogens first. Next slide, please. So from the halogen family, next slide. We all know that fluorine, chlorine, bromine, iodine, and astatine, these all actually combine as a halogen family. Halogen, they are named as because they are salt producers. They produce salt whenever they react with anything, most of the times. Next slide, please. And this is where we say that astatine is not very well known because chemistry of it is not very much well known to anybody. We do not know enough about their reactions. It's also radioactive. So the abundance is not also great enough on the earth crust. So basically when we call off halogens, we most of the times talks about fluorine, chlorine, bromine and iodine. Fine. Next slide, please. And all these are sp2p. You can say when the configuration comes up sp2p5 element, that means they are lacking just one electron to complete their octet. So if they take up one electron, they become absolutely full octet and then they need not to react. Because of the incomplete octet, you can say by one electron, they look forward for such reactions where they get one electron and the octet gets complete. Next slide. Now halogens are the p block elements, and as we talked, next slide, where the only one electron is actually missing up. So that is why if we say that in a free elemental state, the octet should be completed by one electron. Next slide. So in that very case, they can gain electron by two methods. One is the ionic method, where they take up the electron completely from any of the alkali metals and there forms the ionic bond and the halide ion can be actually taken up. Because an excess of electron taken up from maybe any of the alkali will create a negative charge, so halide ion forms. Halide ion means any of the halogen with the negative sign. And other way around, they can do is they can share an electron. How they can do it? They can share it with a single unpaired p electron because they have one unpaired p electron in their p subshell. So they can share it with some other you can say element which has one unpaired electron, maybe the same halogen family only, and they form a covalent bond because it is because of the sharing of the electrons. One electron unpaired is being shared with the other unpaired electron. Both the atoms actually share, both of the you can say subshell get overlapped. So that is why it is a covalent bond. Next slide. Now, high electronegativity and electron affinity is seen among the same period. Period means this way. So if you get to see along this way, in all of the periods, the halogen family is the most highly electronegative because you know electronegative means that they need more or they abstract electrons very easily. Only one electron is required and have tendency to attract electrons. That's why they are called as strong oxidizing agents. Oxidizing agents means that they actually reduce something else. Fine. They reduce the other party and the oxidizing agents they are acting as. They reduce themselves and oxidize the other thing. They reduce themselves means the reduction happens in themselves. Reduction happens in themselves means reduction means they should take up an electron. As I have taught before also, oxidation and reduction is very easy to be understood and remember also. Both the reactions are actually dealing with the uptake or giving up of the electron. In oxidation, if I take up any of the, you can say, metal, it gives up the electron. Fine. However, in reduction, or you can say a metal with a minus sign, this kind of a reaction is observed. Why it is so? because electron should be on the reactant side with reduction. Easy to memorize. R for reactant, R for reduction. So electron should come up in the reactant side. So in reduction, always electron is on the reactant side. And in halogens, because they are actually lacking one electron, they take up electron very easily. So this kind of reaction is more feasible. It's difficult to take out an electron and create an oxidation for any of the halogens. However, reduction is the most favorable condition for halogens because taking up an electron will complete their octet. Rather, going from NP5 to NP4 condition is not a great feasible reaction. They always prefer taking up an electron than giving it up. So performing this kind of a reaction is more, you can say, dominantly preferable. Fine. In that means reduction is more favorable. If reduction goes more favorable, they are the oxidizing agent. Oxidizing agent reduces itself and oxidizes the other. Agent means it brings out that mechanism. If it is oxidizing agent, it oxidizes the other things. Like LIC agent does not buy LIC or for itself. It provides LIC policies for others. So if it is an oxidizing agent, it will oxidize others. Fine. And if it oxidizes other, in lieu of that, it will reduce itself. Always remember this. If it goes with the reducing agent also, it goes that it can reduce rest of the things and it will oxidize itself. So as I told, previous slide please. As I told you here, that it is a strong oxidizing agent. Strong oxidizing agent because they have a tendency to accept an electron. That means they readily get reduced. If they get readily reduced, that means they are very well oxidizing agents. They can oxidize others at the expense of reducing itself. Clear? Next slide. So when it comes to the high electronegativity or electron affinity, the oxidation state, it actually acquires is -1. That's the most probable one. Though it may have many variable oxidation states, but the most probable one is the -1. -1 because if it takes up a -1 charge, the octet gets complete. So that is the most preferred. Most preferred does not mean that the only preferred. There are more variable oxidation states also possible. So the ionic bonds which can be formed with a -1 charge when it takes up an electron from sodium is NaF, NaCl, NaBr, Nai. And so is the covalent bond where the sharing happens. The same electron is being shared by both of the, you can say, atoms. Then HF, HCl, HBr, Hi. All these, you can say, compounds can be formed. Next slide. Next slide, please. So variable oxidation states can happen in all the halogens except fluorine. Why so? Because fluorine among the group, you can see it comes at the top. That means it is the smallest of all. Next comes chlorine. So another shell adds up. So it actually becomes larger in size. Bromine, another shell adds up. So further large size. And the size keeps on increasing. However, for fluorine, you can see that it's low lying energetically. One, it is very small in size. Being small in size, it becomes difficult to actually come up with any other oxidation state than -1 because it does not have a vacant d orbitals where the electrons can move out and we can have variable oxidation states. So except for fluorine, rest of the halogens have variable oxidation states. Else, -1 oxidation state exists for all of the halogens. Next slide, please. Here we'll get to see the oxidation states, various oxidation states. Now, here you get to see that for +1, -1 or 0, what happens? This is NS and this is NP. This is the normal ground state electronic configuration where P5 is there. Fine. So what happens when you provide some energy? The one of the electron may go and get settled in the d orbital. Since fluorine does not have any of the d orbitals, or you can say the subshell is absent in the fluorine because of the very small size, it does not extend to variable oxidation state of +1 or any other state. Fine. It only comes up with the -1 oxidation state. Although chlorine, bromine, iodine, all of them have d orbital, vacant d orbitals lying in between. So that is why they have an availability of the subshell where the electron can move around. Fine. if you want to vacate an electron, you need a space also. Where will it go for the variable oxidation state, right? So this is how you can say +3 oxidation state is formed. 1, 2, 3, right? 3 molecules, or you can say 3 oxidation states are formed, free vacant orbitals. Same goes for the +5. If energy is given, one more electron goes to the d orbital. So creating 3 half-filled p orbitals and 2 d orbitals. Similarly, some more energy is being provided, then s can also be made to go unpaired. And how this you see that 1, 2, 3, 4, 5, 6, 7. So it's wonderful to see that +7, +5, +3, +1, 0 and -1. All the variable oxidation states are possible for chlorine, bromine and iodine. Right? Hence they can form multiple coordinating elements, compounds. Next slide. Here are a few examples. Like chlorine, you know that valency of any of the halogen would come up to be 7, 2 for S, 5 for P. So if we start counting the number of electrons or the lone pairs, 1, 2, 3, 4, 5, 6. The 7th one forms a bond leading to a +1 oxidation state. Here again, you get to see 1, 2, 3, 4, leading rise to 2 lone pairs. A pair of electron leads to a lone pair, right? So here we get to see the paired electrons are giving the lone pairs. 3 are left and double bond with oxygen, single bond here with oxygen, leading up to 3 +3 oxidation state, right? Okay, here similarly 1, 2. So our rest of the, you can say bond formations can take place with the valencies 5, 1, 2, 3, 4, 5. So +5 oxidation state. And similarly, +7 oxidation state with no lone pair or no free left electrons. Right? So there are number of compounds possible for variable oxidation states where you can have the same chlorine and hydrogen oxygen with different compositions of acids. This is HOCl, this is HClO2, HClO3, HClO4, varying with the oxidation number. Right? These are all acids. Next slide, please. Now, various oxidation states of halogens and their ions, you can get to see that fluorine molecules only exist in the -1. You hardly see any of them. This is F2, which is a of 0 oxidation state because of the covalent bonding. Fluorine actually gets, you can say, share the electron with itself and forms a 0 oxidation state. Rest, nowhere else you will find any fluorine compound. But rest of the oxidation states are being favored for various substances and various compounds where further oxyacids are actually being formed. This is for +4, +5, +6, +7. So variable oxidation states, because there are more number of, you can say, electrons putting up, which can be actually moved to the higher d electrons or your d subshell. In that very case, we can have till +7, because 7 is the maximum number of electrons putting up in the NS2 NP5 kind of a system. So we have the maximum of +7 oxidation state. Next slide. Fluorine has -1 only as an oxidation state and no other oxidation state, because the most electronegative element and one unpaired p electron available for bonding. So it has -1, right? Next slide. It cannot expand its, you can say, octet because of the low-lying empty d orbitals are absent there. There is no d orbitals. And along with energy required to promote electrons in the third quantum shell is very high. Since it's very small in size. Small in size means that the subshell where the 5 electrons in the p subshell is very close to the nucleus. The smaller size means the same, right? So there is a considerable nuclear, you can say, attraction towards the electron, and they are not allowed to move outside to any of the, or get excited to any of the higher subshells. Fine. So that is why the smaller size, like for example, for fluorine, what happens? This is S, 2 electrons are there. If this is P, however, for chlorine, many more subshells comes up, and then comes this kind of electronic configuration comes up. Some more inner, you can say, electrons are filling in, and then comes the outer electron, the outer valence shells. So in doing so, this nucleus actually attracts these electrons very tightly, bind it very tightly, and does not allow them to move out on excitation or providing any kind of energy. However, the distance of separation becomes larger for chlorine, fluorine, and bromine because of the bigger size. Inner lying filled orbitals actually kind of screen them from the nuclear attraction, and because of which now they are free to move, so they can move also. The non-availability of d electron is one of the reason. The other reason is they are very close to the nucleus, so the nuclear attraction does not allow them to move out as well. However, they are being screened. Screen means cover, or you can say they are being spared or saved by the inner lying electrons. The force of the nucleus is more dominant towards the inside of the shell, subshells. As it goes outer, thus you can say attractive force becomes weak. So that is why they are more probable or preferred to move to the next orbital while providing the excitation energy. So that is also one of the great reason that fluorine cannot have any variable oxidation state apart from 0 or maybe -1. However, chlorine, bromine, iodine may have up till +7. Fine. Next slide, please. Now, the next point which comes up is about the melting and the boiling point. Melting and boiling point increases as we go down the group. As you get to see that melting point is also increasing and the boiling point is also increasing as we are going down the group. Next slide, please. Now, what is the reason behind that? As we go down the group, you get to see that the melting and boiling point both are increases. It's because the molecular size also increases down the group. Fine. What happens during a melting or a boiling condition? It says that electron cloud is more easily polarized. Polarized means it is actually among the whole of the polarity is being created. Fine. Induced dipoles are formed more easily. Fine. And because of it, stronger London dispersion forces act upon. So because of which, as the size increases, the melting and boiling point also increases. Fine. Next slide. Now, the another property, we are talking about the physical properties of halogen. We need to talk about the color becomes darker down the group. When you get to see fluorine as a gas, or you can say chlorine, bromine, iodine, these all are colored compounds. So pale yellow color for fluorine, greenish yellow for chlorine, reddish brown for bromine, and iodine becomes violet black. So as we move from top to bottom of the group, the color intensifies. Fine. Next slide. Here you get to see in pure form, these are the color formations. In water, it gives this color. Water being, you can say, non-polar compound, this kind of coloration is given. And polar solvent like 1,1,1 trichloroethane, some other color is found. So every time, if it is a polar compound or a non-polar compound in which the halogen is dissolved, it gives a specific color, a different color. Right? It's for the same iodine, it's violet black when it is in its pure state. It's yellow only and slightly soluble in water. However, it's violet for 1,1,1 trichloroethane. Right? So color keeps on changing depending upon the solvent it is dissolved in. Now, color, why it actually gives color? Halogen, because it is non-polar molecule. Right? That is the reason it does not dissolve well in polar, you can say non-polar molecules are there. So it's not very soluble in polar solvents such as water. Itself being non-polar means there is no polarity between them. So what happens? It does not dissolve very well with the polar solvents. Water being inorganic has a polarity. It has a lone pair at one end and the bond pairs at the other. So it has a polarity. So it does not dissolve very well with, you can say, polar solvents like water, because the universal rule is like dissolves like. Polar will dissolve polar, non-polar will dissolve non-polar. Polar means being mixing up, or dissolving means mixing up, getting comfortable with each other, like you guys become comfortable with your kind of persons and don't get very comfortable with different kind of people. So polar is one class of people, non-polar is one class of people. So all polar molecules will actually dissolve very well, fine. Like you will get to mix or solubilize. Mixing is solubilizing. Solubilizing means the mixing only. And when you solubilize sugar in water, that means you mix it. And it should be actually one. Fine. So in that very case, we get to gel with those who are like us only. With different people, we don't gel well. Fine. Attraction is something else. But mixing means solubility. Always remember. So solubility comes up with the same kind of people or same kind of molecules. So polar will dissolve polar, non-polar will dissolve non-polar. But polar and non-polar won't dissolve very well. Fine. So halogens being non-polar molecules, they are not very soluble in polar molecules. However, in organic layers, they are very soluble because most of the organic molecules are non-polar. Because of the carbon moiety, polarity is not generated. Polarity generates in ionic substances. So it comes up in the inorganic species. Right? Next. Like you get to see the colors of halogens in water. Chlorine, bromine and iodine, they all have some colors. Here it is chlorine, this is bromine and this is iodine. Different color formations comes up because of the difference in the solubility as well. Fine. Next slide please. And trichloroethane, 111 trichloroethane, it gives different colors. Iodine wasn't giving the violet color when it was dissolved in water. Rather, the solubility was also to a very less extent. Next slide. Now, electron affinity. Electron affinity, what does it mean? First of all, we need to see that electron affinity is following a trend. Trend where fluorine, chlorine, bromine, iodine along going down the group, chlorine onwards, it's actually decreasing. Fine. And it's maximum for chlorine. And for fluorine also, it's decreasing. Rather, going in the same side, it should be highest for fluorine, but it is not so. Why so? Next slide. The number of electron shells and size of electron of the atom increases down the group. That's very true. But the nuclear attraction for the additional electron decreases down the group. Nuclear attraction, as I told you when I made this diagram, I told you guys that as the screening molecules or electrons come in between, they actually here you can see in fluorine molecule, since the nuclear attraction is very dominant for the unpaired electrons outside also, being in the close proximity. However, for chlorine, bromine and iodine, the attraction becomes lesser. So affinity for next electron should actually be like electron affinity should decrease from chlorine to iodine, because whether the octet gets complete here or not, it's okay for it. Fine. Electron affinity means that the octet should get complete. Does not really matter as long as the shell goes on farther and farther from the nucleus. However, the trend does not follow for fluorine. It should have been highest for the fluorine, but it's not so, because if I need to accommodate one more electron over here in this very subshell, being the smallest in size and already accommodating 5 electrons, will actually create a kind of a crowding. So because of which it will experience an repulsion from all the neighboring electron as well. So only in the case of fluorine, the electron affinity lowers. However, the trend should be that the electron affinity should decrease down the group, because as it goes on farther and farther from the nucleus, the need of an extra electron to become equivalent to the nuclear and the electronic charge reduces because it is far enough. But the trend is not the same for fluorine only. Fluorine does not have the highest electron affinity only for the reason of the very small size that incoming electron will experience an electronic repulsion from the neighboring, you can say, small size shell putting up with 5 electrons. So that is the reason the trend goes like for electron affinity, that the electron affinity is maximum for chlorine and it goes decreasing down the group. But only exception comes up with fluorine, which is not at the highest electron affinity because of the small size, and the smallest subshell putting up already 5 electrons does not allow an extra incoming electron or does not welcome with that great power because there is already a crowding. Small subshell already putting up with 5 electrons. These are the bigger subshells. The outer electrons being putting up in chlorine, bromine and iodine are the bigger subshells. So the electrons putting up already have enough space. However, fluorine being smaller in size, already accommodating 5 electrons in the outermost one, does not actually really appreciate coming up of the next electron. Already they are overly crowded. So it's only with the fluorine that the trend takes a reverse order. And chlorine becomes the highest in the case of electron affinity. Fine. Electron affinity, the term itself is the affinity for an extra electron coming up. So it should be maximum for the fluorine, but it is not so. So it goes for the chlorine, the maximum. Clear? Next slide, please. Now, the atoms of fluorine have smallest size and the same interpretation has been given. So fluorine has the lower electron affinity than chlorine and bromine. Right? Next slide. Next property is electronegativity. Electronegativity means the term that electronegativity, that it has a tendency to accept the electron. Fine. The tendency though goes this way. Next slide, please. Where the number of electron cells and size of an atom increases down the group. So electronegativity decreases down the group. Most should be for the fluorine as the trend was actually expected. The nuclear attraction for the bonding electron decreases down the group. Fine. Because it is not about accommodating an electron itself, it is about forming a bond with an electron. So now fluorine does not have any problem because it does not need to actually accommodate in the subshell, rather needs to bond and have an electron, getting an octet complete. So it will have a high electronegativity unlike the electron affinity trend. Electronegativity and electron affinity are two different things. Fine, getting it? So it need not to accommodate in its own subshell, but only to bond with an electron. So bonding with an electron, the electronegativity is quite high for fluorine because it does not need to accommodate in the same subshell. Clear? So the trend remains the same as it goes down the group, it decreases, and it is maximum for fluorine for electronegativity. Clear? Next slide. Fluorine has the highest electronegativity because it is most reactive element. So that is also very clear that as we go down the group, the reactivity decreases.